So what you're looking at here is a simply supported beam with point loads and uniformly distributed load, UDL. And what we're about to do is to draw the shear force diagram and the bending moment diagram. And just before we do this, we need to be able to calculate the reactions at RA and RB. But I am not going to go through the calculations of the reactions because I've done a video on doing that with this exact question. So if you don't know how to calculate the reactions, then please watch this video right here, popping up in the top right corner, or if you don't see it, check the description and then come back and look at how we draw the diagrams. So I'll give you the reactions for the calculations that we did previously, and at RA that was 17.67 kilonewtons. And for RB, our reaction was 19.33 kilonewtons. Now, what we are required to do, we need to draw our shear force diagram. But before we draw the shear force diagram, we need to understand first of all what the points look like that we're going to plot. And I'm going to break that down for this particular video, just because we have this UDL and I want us to be very, very precise with what we do. So let's break down the shear force diagram coordinates. So for the shear force diagram, the first point that we're going to be interested in, starting from left to right, is that point at 0 meters. And 0 meters is right there where our reaction force is. And at 0 meters, we have that 17.67 kilonewtons. So that's the first point we will plot. And then we move on to the next point at 4 meters. And at 4 meters, we're going to end up with 17.67. That would be going up. And we need to subtract that 5 kilonewtons that's going down. So the point or the coordinate that we would be left with is 4 meters, and that should be plotted at 12.67. So the next point is going to be at 9 meters. So at 9 meters. So because at 9 meters we would already be at 12.67, then we would just be going down again by another 19 kilonewtons, and that would take us into the negatives. So we would be at negative 6.33 kilonewtons. So for the UDL, we're talking about just before the end of the UDL, right there at 14 meters. And for that, it's going to be the value of the point load that we use. So if we would already be at negative 6.33, then when we look at the UDL, it span across 2 kilonewtons per meter across 5 meters. So it means then that that would be 10 kilonewtons. So we would be going down by another 10 kilonewtons. So that would take us to negative 16.33 kilonewtons. And then the next point that we are interested in would be happening right there at the very end of the UDL again. So we have another point at 14 meters, which is exactly where that next force 3 kilonewton is acting. So we would already be at negative 16.33, and we would need to now go down by another 3 kilonewtons, and that would take us to 19.33 negative. And then now for the final point, which is the reaction point there at RB. So we would now be at 18 meters. So at 18 meters, that reaction point is going all the way up back to 0. So from minus there, 19.33, and there would be plus 19.33. So that takes us now back to 0. So just to highlight the points that we are going to be plotting. So first point right there, 17.67. Then we move down to 12.67. Then we move down again to another further negative 0.63, negative 6.33. Then we move down to negative 16.33. Back down to negative 19.33. And then up to 0 kilonewtons. So let's plot those points now and see what they look like. So here we have everything nicely organized. We have the coordinates that we have calculated previously, and we have the grid ready to go for our points to be plotted. So let's get right to it. So the first point is 17.67 kilonewtons at RA. So let's plot that. That's right there. Second point at 4 meters, we now come down to 12.67. So that will be round about here. Moving across to 9 meters, and that comes all the way down to negative 6.33. And then we'll come across to the 14 meter mark. We have our UDL, and we need to be very careful with how we treat that one, which I'll explain as we do it. So that's negative 16.33, which is acting somewhere there. And then on that very same point, 14 meter mark, we have another point there, which is 19.33, which we need to mark on that same line around there. Then we come across now to that 18 meter mark, which takes us back to 0. So let's look at how this should look. So as expected, from 0 all the way up to our first point. Then we need to go across to the 4 meter mark. Then come down to that 12.67. Then we go across to that next point there, which is our 9 meter mark. Then we go down to the negative 6.33. Now for the UDL, because it's happening gradually, we need to reflect that using a diagonal line. So we will not use a straight line across. So that will look something like so. And then we go down directly to the next point, negative 19.33, and now across and back up to 0. And as always, if you want to, optional, you can shade in the area that you're interested in, which would look something like this. There you go. So special attention should always be placed with the UDL because it's the only unique force aside from the other point loads, and the line that we draw to reflect that gradual loading is that diagonal line. So that's one key point to note. So now we're going to go across to doing the bending moment calculations, and of course we plot those so that we get the bending moment diagram and we can see exactly what that looks like in the next few minutes. So let's now do the bending moment calculations so we get those values to plot our points. So again, it's going to be similar to what I've explained. We are going to be starting from RA right here. And each time I draw this blue line, what we're interested in is everything to the left of that blue line. And any force that's trying to rotate the system using the blue line as a pivot point, any force trying to rotate clockwise, we're going to take that to be positive. Any force going counterclockwise, we're going to take that to be negative. So at RA, that's going to be at length 0 meters. And what that means is we have no bending moment because the bending moment there will have to be 0 because our distance is 0 meters. And just in case you don't know, the formula we're using to calculate bending moment is just moment equal to the force multiplied by perpendicular distance. Good, so that first point then is done for the bending moment. And now we're going to go to at point 4 meters. So at 4 meters, I'm going to draw that blue line once again so you can see all the forces to the left of the 4 meters. And there is only one force acting to the left of the 4 meters. And if you can already see that it's the reaction force, then you're in business and you understand what's happening. So that reaction force, which we calculated previously as 17.67, its distance from that blue line is 4 meters and it's trying to rotate clockwise. So we'll use that as a positive value. And what we get there is 70.68. And that unit is kilonewtons meters. So now the next point that we're going to move up to will be at 9 meters. So then at 9 meters, what do we have to the left of that blue line that I will draw in a second? So there is our blue line, and to the left of the blue line, what we have there, we have the reaction force, and we also have that 5 kilonewtons force. So at that 9 meter mark, let's do some analysis. So that 17.67 is now going to be much further away. It's going to be now 9 meters away. So that's the first thing that you should take note of. And then the second thing is that 5 kilonewtons is going in the opposite direction. So it means that will be negative because it's going to try to rotate counterclockwise. And the distance of that 5 kilonewtons from our pivot point is 5 meters. So it's 5 times 5. And those are the only two forces. And that turns out to be a total of 134.03. And that's kilonewton meter. So that's the second point. Moving on now onto the next point, and this is where I needed to pay very, very special attention or close attention here, because for the UDL, what we usually do is to break up the UDL so we get a good reflection of what's happening. And for this one, because it's only 5 meters, so it's span between that 9 meter mark and all the way up to the next checkpoint there, we are going to break this down into the middle right there. So that's at 2.5 meters in the middle of the UDL there. And let's do the analysis now. So what are the forces we have to the left? So of course we have this RA value. We have this 5 kilonewtons value. We're going to have that 19 kilonewtons value. And we're going to have the UDL span, but only across 2.5 meters because we're going halfway between first. So let's do the calculations and everything should be quite straightforward just as before. So now this is going to be at 11.5 meters. So at 11.5 meters, what we still have that 17.67, but its full distance now is going to be 11.5. And everything else is now going to try to go the opposite direction. So now we're going to have first that 5 kilonewtons, and its distance now is going to be 5 plus 2.5, which is 7.5. So times 7.5 minus again that 19 kilonewtons, and its distance is going to be 2.5. So that's 19 times 2.5. Remember, the distance is from that blue line. And then minus now, this is going to be the UDL analysis that I'm talking about here. So for the UDL, what we have is 2 kilonewtons per meters. So that's going to give us 2 multiplied by the span, which is 2.5. So that's representing the force of the UDL so far. But now we need to place the UDL in the middle of that 2.5, which is going to be placed at multiplied now by 1.25. So that's the UDL. So just to reiterate this bit that I'm highlighting in green. So what we have done, we have split the UDL into 2 for analysis purposes. So right there, I'm highlighting in green on the beam, that length is just 2.5. But the UDL itself, it spans 2 kilonewtons now across 2.5. So hence, we have that 2 times 2.5. But how we treat UDL as a point load is we need to put it in the middle of its span. So the middle of that 2.5 span is that 1.25 that I've used to multiply. So that's the analysis for the UDL. So when we sum all of this bit up now for the UDL, the total gives is 112.0, and that's kilonewtons per meter. So then, because what we have done so far is the UDL just half point, what we need to do now is to do the full UDL. So I'm going to now put my blue line at the very end of the UDL, and that's the analysis that we're about to do. So that's the blue line at the end of the UDL, and all the forces that we have acting to the left of that blue line will be our RA, our 5 kilonewtons, our 19 kilonewtons, and of course the entire UDL itself. So let's do that calculation now. So this will now be at 14 meters. So then at 14 meters, again, we have RA, which is our 17.67, multiplied by the full length of 14 and minus now the 5 kilonewtons. And for the 5 kilonewtons, that's now at 10 meters. Go across now to the 19 kilonewtons, so minus 19, and its distance is now at 5 meters. And minus now for the UDL again. So this time for the UDL, once more, we have the UDL 2 kilonewtons per meter span across 5 meters. So that gives us that 2 multiplied by 5. And then we need to place that now in the middle of the 5 meters. So we need to multiply that now by 2.5. So that's the UDL. And finally, when we do the sums, we get that to be 77.38 kilonewtons meters. And then now the final point is going to be at 0.18 meters. And as you have seen before, at 18 meters, we should expect to get a bending moment of 0. So I'm not going to go through that calculation as I've done before. I'm just going to put that 0 in, and you can check out the previous video where I've proven that bit. So we're going to organize this nicely now and just plot the graph for our bending moment diagram. So we have our diagram ready to go. We have all our calculated points ready to go. We now just need to plot them, and we're going to do just that. So at point 0, we have our point right here, plotted at 0. Moving across to 4 meters, we need to go up to 70.68. And bear in mind, this is just an estimation, and the purpose is just for you to see what the diagram should look like. Then we have across to our 9 meter all the way up to 134. So I'll squeeze that all the way at the top. We have across to the midpoint of the UDL, which is the 11.5 meters. We come back down now to to the midpoint now of the UDL, we come back down to 112. So somewhere around here to point 14, which is the end of the UDL. We're going to come back down right here at 14 meters. So at the end of the UDL now, we're going to come back down to 77.38, around there. And then to the end, we come back to 0. And all that's required of us now is just to plot those points using lines. So that's it for the UDL. So if you have found any value from the video, please share the video to someone who might need the help, and subscribe to the channel to help me to grow and reach as many people as possible. And I will see you in the next video.